Okay, this is chapter 14, and we will start talking about regression analysis, and this is going to be for two chapters, chapter 14 and chapter 15. In this chapter and the next chapter, we are going to study the relationship between two or more than two variables. So the goal is to study the relationship between multiple variables. For example, someone is willing to look at the stock price versus the dividends. Do we have a relationship between these two variables? If the stock price goes up, do the companies pay more dividends or something, or no? Maybe someone's looking for a relationship between the product sales and the amount of money spent on ad. So the money, if we spend more money on ads, are we going to make more sales or something? So, people are willing to study the relationship between multiple variables. We may go further, actually, study the relationship between more than two variables. Like you would like to know the market value of a home. So what you're going to do, you're going to look at multiple variables. Maybe you're going to look at the selling price right now, the size of the property, the age of the property. Maybe you can add more, like the number of baths, number of beds, number of garage, and so on. To study the relationship between multiple variables, we are going to start with very simple models in this chapter and study the relationship between only two variables, variables. The first one, we're going to call it response variable or the dependent variable, and the second one, we're going to call it the predictor or the independent variable. In chapter 15, we're going to expand. We're going to expand and have more than predictors or more than independent variables. So the first thing we start with when you investigate the relationship between the variables, the first thing you have to do is to look at something called the scatter plot. It's very simple. Just you want to look at the correlation plot. Okay, the scatter plot these are scatter plots. It tells you just the relationship between the two quantity. And by the way, if you look at the scatter plots, we have dots. So we assume that both variables are numeric. Okay, both of them are numeric. So this scatter plot represents the relationship between the two variables. And as you see, we have a positive relationship, linear. It looks linear because it's roughly a line. It's roughly kind of run. And actually, it's increasing relationship. It's increasing positive linear relationship. However, this one looks negative relationship. It's negative and decreasing. Why decreasing? As x increases, y decreases. Look at this dot. As x value is small, but y is large. If you go here, x is large, y is small. So this is a decreasing relationship. It's a linear relationship. For example, this one is not linear. It takes a curve kind of relationship. It's not a linear. And this is also another curve. This is a decreasing curve. This is an increasing curve, right? And by the way, this is a strong relationship. It's a strong positive linear. So look, we have more than one word to describe this relationship. It's a strong positive linear, okay? And this is a strong negative linear. It's a strong actually because it's decreasing all the way. It's linear. This is also, it's a strong but non-linear. It's a strong relationship and it's non-linear. We have kind of a pattern. We know the pattern, so that's why it's a strong actually. And this is also a strong, but it's not linear. It's increasing, but it's not linear, right? This is something else actually. It's a different mathematical equation. If you look at this scatter, you cannot tell what's happening because sometimes when x is small, y is small, x is small, y is large, and it's kind of doesn't take any pattern or any shape. So we say that there is no relationship, and precisely we can say there is no linear relationship. And there's no linear relationship. Actually, this one you can pretend that there is a line here, increasing line. There's a decreasing line. There's a curve here, and there's another curve. But this one you can say nothing about it. Actually, the same thing with this one. Someone's going to tell me it's constant. It's constant horizontal line, so it's zero. There is no relationship. Zero. It's fixed. As x increase or decrease, y doesn't change. There's the meaning of that one, right? So we don't have any relationship in these last two figures, okay? Because no patterns and no connections. Normally, the x value, the x variable, we have two variables again. Variable on the x-axis, variable on the y-axis. The variable on the x-axis is going to be the predictor or the explanatory variable. And this is the variable that is going to be used to explain the variation in the dependent variable, okay? However, the y variable is, we will be calling this one dependent variable. The dependent, or another word, is the response variable. This is the one we are looking, or the variation of this variable that we are willing to explain. Okay, so we have two variables, the dependent and the independent. So let me write these down. Okay, so the dependent and the independent. And the dependent or the independent usually is on the x-axis, and this is on the y-axis. Okay. Now we're going to start with doing one example, and this example is going to last for the end of this chapter. So we're going to investigate multiple ideas using this example. A regional retailer would like to determine if the variation in average monthly store sales can be explained by the size of the store measured in square feet. So actually this is the core point. Okay. So it seems that the goal is trying to understand or to know whether the variation in the one of the variable, which is the average monthly store sales, can be explained by the size of the store measured in square feet. So I'm going actually to delete one word. I'm not going to delete it for the sake of deletion. I'm just going to hide this word because I don't want this word to confuse you, but we're going to keep it in our mind. So we're speaking not about the monthly store sales, it's about the average, because we cannot pick that number exactly. Just I'm going to delete this one for now, okay? So we are studying the relationship between two things, the monthly store sales and the size of the store. In other words, if the size of the store is big, so we sell more, or the opposite, or what? So what we do to answer this question, to study the relationship between these two guys, these two variables, we took a random sample of 21 stores, and we have the information about two things, the store size and the monthly sales, the average monthly sales, or the monthly sales, okay? Again, the average is going to be a confusion here, so I'm going to delete the average. And you can find this in Excel and in Blackboard. There are two sheets, don't get confused, okay? Two sheets there. So we're going to answer this question, and we're going actually to do a scatter plot and study the relationship. Before we do that, I'm going just to move on to the second idea and get back to that question, and we do them together. When we study the relationship, actually, sometimes we are having a linear relationship, a positive linear, very strong. This is a perfect, actually, not strong. This is perfect. We need a mathematical quantity that tells you how strong is the relationship between the two variables. This quantitative measure, we call it correlation coefficient, the correlation coefficient, which measures the length, the strength of the linear relationship between the two variables. The linear, this is important. It studies the strength of the linear relationship between the two variables. It's a quantitative measure. It ranges from 0 to 1. From -1 to 1, from -1 to 1. And this looks very perfect. It's perfect, not strong, perfect, because all points lies on the same line, actually. So because this is very perfect, so the value has to be the R value, the coefficient, the correlation coefficient R is going to be a positive one. So positive one means it's a perfect positive relationship, R is -1. It's a perfect negative relationship, perfect negative decreasing relationship, okay? This is kind of a linear, but it's not perfect, but it's still good. Actually, you can still find a line that passing through most of the points or something, right? Maybe this line is good somewhere here. So this is kind of a strong, we can see a pattern, increasing pattern. It's kind of linear, and the pattern says it's increasing. Yeah, it's increasing linear, okay? Maybe we have some kind of, maybe you can consider these like outliers, fine, but at the end of the day, we have an increasing pattern, right? And this is R 0.7. So in general, this is a positive. So we have a strong relationship, strong. Also here we have kind of a moderate negative relationship. It's decreasing, but still the points has more scattering, shape, right? So the question you may ask, let me finish, then we talk about this. If you look at this pattern, it's actually, there's no relationship, nothing. We don't know what's happening. There is no X and Y X does not depends on Y, or Y, do not depends on X. Y is always changing. Even X is get from small to large, nothing is changing with Y. Y do not rely on X. So the relationship is 0. The coefficient is 0. Also, this is not linear. Okay, it's taken parabola shape, right? Parabola. So it's not linear because this coefficient, this correlation coefficient, study the linearity, the linear relationship. Also R is 0. So R between -1 and 1. If the value goes to 1, positive 1, then we have a strong and perfect positive relationship. If the value of R very close to -1, so we have a strong negative relationship. If the value of R is, let's say, between 0.6, 0.7 and above, strong, between 0.5, 0.567, so this is moderate. And if we have a negative value, the same thing, let's say this is -0.5, it's a moderate negative relationship. If the values of R are getting closer to the 0, then we say there's no relationship. no relationship. And if the points, if R is 0.3, it's a weak linear relationship, weak. So you can kind of look at this behavior, okay? So for the same example that we started with, we would like to study the relationship between the store sales, monthly store sales, and the size of the store measured in square feet. We're going to see the relationship. We're going to do the scatter plot, and we're going to describe this, and we're going to find the correlation coefficient of this, okay? The correlation coefficient of this. So before that, we have to write something. We have to understand why we are doing this work. We would like to study the relation between the monthly store sales and the size of the store measured in square feet, okay? And what is the dependent variable, the response variable? What do you think the response variable is? Which one relies on the other one? Do you think that the dependent variable is the size of the store or the monthly sales? Which one is the dependent? Which one is responding to the other one? The question says if the variation in the monthly store sales can be explained by. So can we explain the variation of the monthly store sales? This is the whole, okay, let me change the color. This is going to be my dependent. Can we explain the variation of the monthly store sales by the size of the store measured in square feet? So this is going to be the monthly store sales, because the questions already said that this to you. Can we tell something about the variation in the monthly stores just by looking at the store size? The independent variable is the size of the store, okay? Okay, nice. So now we are going to go to Minitab, and we're going to go to Blackboard, copy the data, and paste them on Minitab. After that, we're going to construct this scatter plot and look at the R, okay? So what to do, we go to Stat, Basic Statistics, then we go to Correlation, and we are going to select these two values, and we are going to go to Options. We're going to keep Pearson correlation. We will be talking about this one in a second. I'm going to keep it 95. Graphs, I'm going to choose correlation and p-values. Also, for the results, I will touch nothing. Then, okay. So we can actually look at that, and we can do a description. Okay. Oh, what is that? Okay. So what do we have here? We have actually, it's clear that it's a positive relationship, and it's a strong positive relationship. Strong positive relationship. We can see obviously that it's increasing in a linear fashion. So we have, there is, okay, fine. There is a strong positive relation between the store size and the monthly, again, we said average, right? Keep it in your mind, store sales. So because the independent variable is the size of the store, it's on the x-axis, and the other one is on the y-axis, okay? Also, we would like to look at the second idea. The question says calculate the sample correlation coefficient, and this is an important word, by the way, between the store size and the average. Actually, we did here. We did found the scatter plot, and we found the R. Look at R. R, by the way, it's a good idea here to say. Where is it? It's R. Correlation coefficients R. This is the sample correlation coefficient. The little R. This is the sample R. What about the population one? The population one, we call it, by the way, we call it raw. Okay, raw. So now we are studying R. In this example, we are studying R because we are finding the relationship between the two variables that we have a sample data from the sample, right? We have no clue about the population. That's why we took a sample, simply. So in this one, what is the, to answer the second question, which is calculate the sample correlation, we did already. So R is supporting your visual representation, right? So R is equal to 0.81851, which is actually tells you that it's a strong relationship. It's a strong relationship. And actually, if you just scroll down, we're going to see the correlation is 0.85 is the number that exists on the table, okay? Now we have an issue here. What is the issue? Because this R is based on the sample, right? It's based on the sample. Because it's based on the sample and it's subject to the sampling error, what we have to do a formal hypothesis testing. Every time we go back to the hypothesis testing, because we claim that there is a strong positive relationship between the store size and the sales, the monthly sales. Now you have to test this one. Is it due to sampling error or no? This is really a correct relationship. So what we have to do a two-tailed test in this question now. Or if we are concerned about the two-tailed test or one-tailed test, the hypothesis is going to be different. So if you want to know whether there is a correlation or no, the null hypothesis is going to be there is no correlation between the two variables. We assume that there is no correlation. The alternative hypothesis is going to be there is a correlation between the two variables. If we are looking for the one-tail test, for a study the direction, if you care about the direction of the correlation, it's going to be one-tail test. Okay, so let me first type all of these things. Okay, so the value of R, as we said, it's based on the sampling error. It's on the subject to the sampling error. We need to conduct hypothesis testing. And for the two-tail test, we're going to do the following. This is case 1. And we are the null hypothesis. The null hypothesis is going to be, this is the null hypothesis. This is always going to be something like this. What does this mean? That there is no correlation. However, if you're talking about the alternative hypothesis, then it's going to be rho is not equal to 0. So there is correlation here, and there is no correlation between the two variables. Okay, so this is the case of two-tail test. If you care about one-tailed test, we do the following. This is B. For a one-tailed test, you look at the direction. Okay, so if you are interested in the direction of the correlation, what is the null? The null is going to be, actually, one of them is going to be greater, the other one is going to be less. So this is going to be maybe greater than or equal. This is going to be, this is going to be less than, yes. If this is right tail, so this is for the right tails, right? So for the left tailed test. Because we said for one tail test, we have left tail, we have right tail, right? So if this is right tail, there is actually no correlation between the two variables. Someone's going to tell me why it's a greater than. I'm going to tell you this. There is a negative linear relationship. By the way, I forgot to write my linear relationship. So there is no correlation or linear relationship, actually, because we're studying the linear relationship, right? And here the same thing. I'm going to say linear relationship. And so there is no correlation or linear relationship between the two variables. For the alternative, we have a negative linear relationship between the two variables. Okay, and this is the default scenario. It's okay that we write them greater than or equal, but actually we assume that there is no correlation. There is no correlation. For the right tail, you have to do the opposite, as we learned multiple times. Okay. So now for this one, and what is the degree of freedom is n-2. And this is the t-test, actually. This is the t-value. How to find the t-value? We're going to do it manually. So in the question of the homework, this is the t-test. You have to do this manually. I think okay, let me check if we have it here or no. But in this one, we have the p-value, by the way. So what is the n? Is the number of the sample size, or the sample size minus 2. What is r? R, the value we got already. We know the n. We do manual calculations. Very easy to get the t-test value. We use the t-test value, okay? And so we have two assumptions here. The data has to be interval or ratio, numeric, okay? And the two variables, are the x and y have to be pi variate normal distribution. Okay, the t-test assumes this condition already. So they have to be bivariate normal distribution. But again, the t-test is a robust test. It's correct. We still can use it, and it gives some good conclusions, okay? Sometimes we have a slight departure from the normal distribution assumption, but that's okay? So although the t-test assumes the bivariate normal distribution, it's still robust. And it is correct, or it gives correct inferences with having a slight departure from the normality distribution. So for this question now, the same question, we did this. We found there is a positive relationship based on the sample, and the R was 0.85. Is that statistical significant? Is it statistical significant or no? And actually the question is going to be, determine if a positive correlation exists. So we're looking for what? We're looking for right tail test. Let me change this and keep it 5%, actually. 5%. Level of significance, which is alpha. So is it positive relationship between the two guys or no? So what can we do? This is a right tail test. This is a right tailed test. Because since we test whether there is a positive relationship. Okay. So what is the null hypothesis and the alternative hypothesis? This is for the left. I'm going to copy these and change them because we are looking for this is going to be less than or equal, or actually equal 0, and this one going to be greater than or equal. Sorry, this one going to be greater than. Yes, there is a positive. There is a positive, and there is no correlation between the two variables, and there's a positive linear relationship between the two of them. Again, someone's going to tell me why you did not write greater than here, less than or equal. Again, for the null hypothesis is the default scenario. No relationship. The equality is the most important part, the equality. Okay, so can we get this? Yes, we actually have the p-value. Look at the p-value here on the left, the chart we got. So the p-value is what? P-value is 0. P-value is very small. P-value is 0, which is less than what? Alpha, which is 0.05. So what we do, p-value is very small. So the test value is in the rejection region. So we reject the null. If you reject the null, that means we conclude that there is a significant positive, statistically significant positive correlation between the monthly sales and store size. The monthly size and the store size. Sales and the store size. The question is, can we do the thing, can we compare the t-values? Let me do this because you will be seeing this in the homework questions. So let's calculate the t-value, by the way. So t-test. I'm going to use the formula, by the way. The formula says, if I remember, yes, it's r divided by square root of what? 1 minus r squared, I remember, divided by the n minus 2. Here we go. Now we plug in these numbers. What is the r value? The r, the correlation coefficient, 0.851 divided by, let me copy this. So it's 0.0851 squared. I have to put them between parentheses, by the way. And what is the number of the data? I remember they said 20 or 21. Let me go up here. Now the question says you have 21, sample of 21 stores. So we have 21 stores. So 21 stores. Then we do the manual calculations for this. Let me do it here in my calculator. We got 7.08. So this is the t-test value. This is the t-test value. And we can compare it with a critical value. So we assume, we know that this is going to be greater than the t-critical because we rejected the null. It's a right tail test, critical. So we need to calculate the critical value. We go to graph, view probabilities, it's t-test. Degree of freedom is n minus 2, so 19. It's a right tail, 0.05. So this is 1.729, right? If you study the right tail test, if you do the right tail, 1.729. Yep. So we got to the same conclusion. Okay, so this is again, we get to the same conclusion. If you look at it, t-test, by the way, is 7. 7 is here, actually, it's here. Look at the chart here. So we come up with the same conclusion. Next, we are going to talk about something else. After you explored the relationship between the two variables, you know how strong they are, and it was significant. So this is not due to sampling error. Again, I did not write this actually at the top, that I have to mention that. So the value, yeah, I already said that. What we are going to do, we're going actually, because we said, oh, there is a relationship, there is something that telling us that there's something happening between the two variables, we would like to build a mathematical model, right? So we're going to use this correlation and help us to analyze that relationship between the two variables. So that's why we're going to use something called simple linear regression analysis. What does this say? We would like to see if the single independent variable, how this one will be used to explain the variation in the dependent variable. And it's called simple because we're looking for a single independent variable, because we believe that the variation of the dependent variable is kind of fully explained by only one independent variable. That's why we call it simple linear regression. We know that this is not the case in most scenarios. In most scenarios, we have multiple variables impacting or affecting the variation of the dependent variable. However, this is the case for this chapter. We just have a single independent variable, and we study whether this one explains the variation of the dependent variable or no. We have two models. The first one is the population model, the one that we will never get. This one we have no clue about it. That's why we take a sample, right? So what is the regression model? The population model is why, again, we study the relationship, and it's a linear, it's a straight line. This is the equation of the straight line. If you remember from the high school, y equals plus b or c, This is a linear relationship. It's the same thing, but with different letters, different names, you know. So y equals beta naught plus beta 1x plus the epsilon error. This is the random error term. This is the population model. The problem that we cannot get this guy because we don't know how the relationship between the two variables, okay? The first component, we call it the linear component. This is the linear component. Beta naught plus beta 1x is the linear component, and this is the random error component, the random error component, okay? The random error component. So the question is, how do we come up with this? We will not be able to come up with this, but we are going to use the sample to estimate this model, okay? So how to estimate this model? We are going to estimate this model using this simple equation. We are going to estimate the y, which is the dependent variable, using y hat, which is the predicted or estimated y. We are going to estimate the beta naught by b naught, and we're going to estimate the beta 1 by b1. These will be estimated. We are going to use the sample to produce this equation, okay? We will not be able to produce that equation. However, we are going to estimate these parameters. By the way, beta naught, beta 1, these are parameters. We're going to estimate them, and this is important. Again, we're going to use this in the future. How close we are estimating these guys. How close the b's are reflecting the betas. Are they close, significant? No, yes, what? Because these are the ones that tells you how the line look like, by the way. This is a simple linear equation. We know that this is the y-intercept. The number next to the x is the slope, this is the slope, this is the y-intercept. This tells you where the line cut the y-axis. This one tells you how steep you are going. Steepness, the steepness of the line, right? We're going to talk about this one later. The steepness of the line, the slope, the number with x, next to the x. The number alone is the y-intercept, right? And we are going to study the estimated regression model. Before we move on, these are 4 assumptions we need to take care about. The first one is speaking about the independence of errors. So the first one, short, I'm going to just make it short. The independence of error, what does this mean? So the error for one observation should not influence or be correlated with the error of the another. In other words, let's say knowing the error in one observation provides no information about the error of another observation. So this is in short, the short title of this assumption, we call it independence of, these are very important assumptions, independence of the errors. So the second assumption is the normality assumption, is the normality of the error. The errors at each x follows a normal distribution, just make it simple. The normality of the error, we assume that the errors are normal. So the errors are independent, the errors are normal, and not only this, the errors are constant, the variation of the error, okay? So the errors have an equal or constant variances, okay? The variation or the variance of the errors are constant. What does this mean? The variance or the spread of the errors must remain constant for all values of x, simply, okay? The last one is the linearity of the mean, So we have 4 of them. The independence of the error, the normality of the error, and the equality or the constant variances of the errors. The last one is the linearity of the mean, okay? So you have just to keep them simple without doing all of this. You can type what I said right now. The independence of the error, the what I said, normality, the second one, constant variances, okay, or equal variances of the errors, and the last one is the linearity of the mean, And we can test these quickly, linearity, okay? So we need these assumptions. We're going to speak about these in examples, okay? So now the question says, write the general form of the regression population model representing the relationship between the sale size, the store sales and the size of the store. So what is the relationship? It's very simple. It's y equals, this is a population model. It's y equals beta naught plus beta 1 times x plus epsilon, the error, okay? This one actually, the population model, what is it? What is y? In words, let's write this in words. The sales, right, or the monthly sales, the store monthly sales, the store monthly sales, sales is equal to what? Is equal to the beta naught plus beta 1 times the size, which is x, actually the size of the store, right? Plus the epsilon. Epsilon is called the epsilon. Okay, epsilon. Oh my god. Epsilon. Anyway, I don't want to stuck here. What is the form? What is the sample model? The sample model is the one that, let me copy this. We're going to change them to b's, remove the error. The sample model, the one that we care about, is y hat. Y hat equals b naught. B1, no error. And we have a huge change here. This is not the store monthly sales. This is the expected, actually it's the predicted or the estimated. Oh my God. So let me take, okay. This is the expected. Let me write the expected, predicted, or estimated. So the predicted store monthly sales equals to B1, B2 times the size of the store, no epsilon anymore. Okay. So this is the sample model. This is the sample model. And what is the meaning of the slope? What's the meaning of the slope? The slope is very simple. The slope is from the high school, is the average change in the dependent variable for a unit change in the independent variable. We are going to speak about this. So the slope can be positive, can be negative, can be zero, and it depends on the relationship between the two variables. Also, what is the least square criterion? Is the criteria that determine the regression line that minimize the sum of the squared prediction errors. And what is the residuals? We will be talking about this. Is the difference between the actual and the predicted values of the y. Okay, and we are going to do further investigation about this. And I am going to stop and pause now. We will continue this next class.